So our next presenter is Wolfram Burgard from University of Technology Nuremberg. He heads the lab there on robotics and artificial intelligence. And like Paolo, he is also a winner, although in 2022, 2 years earlier, of the IEEE Robotics and Automation Technical Field Award. Thanks, Wolfram.
Thank you. First of all, I need to thank you for inviting me and having me here in this wonderful line of speakers. And in the next 10 minutes, I'm going to take you through a little bit of the journey of my research career, which has been driven by the idea of building intelligent systems. Basically, we saw this picture yesterday, like embodied systems that can perceive the world and act in it in order to achieve their goals. And throughout my career, I've gone through basically 3 trends, and it started with this probabilistic robotics trend, which began kind of like 1995, almost 30 years ago. Then I moved into this machine learning field, like deep learning and so on, and recently I moved into foundation models, which I'm super excited about, and at the end of this presentation, I will hopefully have convinced you why this is the case. So here's what we started with in robotics approximately 30 years ago, probabilistic robotics. That was the very first work, our AAAI paper, Dieter and I. Dieter is sitting over there, together with 2 students. This is where this idea of using probabilistic representations for navigation and perception actually started. And that led to a couple of developments, and approximately 10,000 days ago, we developed these robots, Rhino and Minerva, that were able to actually act as autonomous museum tour guides in populated environments, basically showing the robustness of this concept. Which then, like 7,000 days ago, led to this book that Dieter, Sebastian, and I basically wrote and worked on for a couple of years, and which then in the end led to this development of self-driving cars. Like at Waymo, Sebastian was basically starting Google X at that time, and where people actually discovered the power of this technology. And Dieter and Sebastian and I actually also became friends. In the bottom right, you see us on the summit of Mount Rainier, close to Seattle. So we actually did not only research, but also had a lot of fun throughout our life. And if you look at why this has been so important, right, this probabilistic concept, it's basically because if you look at the stack of a self-driving car, then you can see that it's particularly suited for several tasks in there, which is basically mapping and localization. Localization we have seen in these museum tour guide robots already, but mapping also was something that started actually earlier, before the probabilistic robotics hype came up. But it was actually then like super active over the past 30 years and actually developed into its solid systems. And here is that the underlying math for this. But in the end, you can actually not only build this for building maps for robots, use this for building maps for robots, but also for other purposes, like, for example, cultural heritage. And this is the result of my startup company, .scene, who's actually doing exactly this, basically trying to reconstruct buildings for cultural heritage in this case. And this is a homage to our friends from PISA as well. And so this has been this probabilistic revolution. And then 5,000 days ago, deep learning came in, which actually revolutionized the perception part, and it allowed us to become way more robust when it comes to the interpretation of the sensor data, basically making sense of your perceptions. And this is basically here, what you can see here, this interpretation part, where you basically know then what the sensor data actually mean. So, and if you look at the complementary aspects, the question is, of probabilistic and deep learning, the question is to how to properly combine them. And this is something that I've been working on together with my students over the past years as well, where we basically try to make proper sense of the output of these deep learning methods in order to combine them properly with the probabilistic approaches. And here's 3 examples. So for example, in semantic segmentation, what you would like to have is basically the network spitting out uncertainties, for example, at the border of the individual concepts, or when it comes to instance segmentation, at the border between individual instances, and when it comes to the combination of that, like the panoptic uncertainties, basically. And if you do this correctly, and this is a challenge because you need to have proper and calibrated uncertainties to combine this with the probabilistic approaches for navigation, then you can actually directly and easily combine them in order to build robust systems. Right? And here's a recent outcome of work of one of my students, Chidich, published 2 years ago, where we are basically combining the deep learning stuff together with the probabilistic one in a natural fashion. So everything is learned here. There's no manual tuning of parameters, of output parameters of these networks in order to actually make the probabilistic approach work. And this is, from my perspective, that's Ken Goldberg mentioned that 2 days ago, where he said it requires a lot of engineering, like still building these autonomous systems. And this is where you basically see where this combination of engineering and learning takes place. But here what we can do is basically combine this in a natural fashion. And then 2,000 days ago, approximately, the foundation models came up. And when I played around for the first time with them, there was kind of like an alert bell ringing in my head. Kind of like this morning when I woke up after this great party yesterday night. Right? So, and the reason for this is that I almost had this impression of, oh my goodness, these models kind of like understand the world. And I will take you through a few examples why I believe this is actually true. And what I want to do is I want to show you the potential of these methods and systems for embodied robots. Right? And there are two approaches right now. The most of the approaches are actually using existing foundation models. That's what I will also take you through, and then I will briefly mention this path towards that what Dieter mentioned in his talk as well, the development of true robotic foundation models that are actually, from my perspective, the next step towards embodied agents. Right. And here's one example of a project that we did over the past years. It's so-called vision language maps for robot navigation, where you can instruct a robot to perform navigation tasks that have been enormously difficult in the past. So for example, what you can tell the robot here, like go to the boxes, or like even harder, like go to the keyboard, right? And we all know that like classifying keyboards is a really, really hard task. So I used to say this is a life of a PhD student, right? This project, like just making the robot robustly go to a keyboard. And in this case, this happens in a zero-shot fashion. There's no learning involved. It's only the large language model that outputs these labels. And here's again an example with a chair. And in the background, you also see a plant. Right? Imagine you ask your student to program a classifier for a plant. Right? He has to label thousands of images in order to do this in a robust fashion. And these large language models like do this in a zero-shot fashion and basically, apart from energy use consumption, for free. Right? And you can use them also for SLAM. And here's an example of that FM log paper that we published 2 years ago with my student Ray Hane, where you basically use the language embeddings to solve the data association problem. And the advantage of this is, if you look at these image retrieval tasks here, is that you can solve this data association question, like is this the same place like I saw before, through these language embeddings, and even when you have substantial viewpoint changes or illumination changes. Right? So language provides you with an enormous robustness in the description of these scenes in order to solve these localization tasks as well. Give me a second, and the advantage of this, and on top of this, is that you can also use this for instructing robots about which objects to focus on in a navigation task. So this is not only semantic SLAM, it is also, like, I call this language-instructed SLAM. Right? You can tell the robot, in order to navigate in Wolfram's department, right, focus on the fire extinguisher or these like green wall things or posters that we have on the walls. But you can also use these models for basically programming robots. And this is work that I did with Oyer 2 years ago. He's in Berkeley right now. And where you basically prompt the system with the individual actions that the robot can execute, and then tell it, like, tidy up the workspace, and then from that, it automatically generates a script allowing the robot to perform that particular task. And this is something that you can see here in this video, where, like, in a zero-shot fashion, the robot is actually able, apart from learning the individual actions, right, come up with a solution to that task of cleaning up the workspace. And finally, like, as one of my coolest works over the past years, at least from my perspective. We talked about, or we heard interesting discussions about grasping as well. And when I played around with these models, I've wondered, like, can I use this for grasping as well? And fact is, yes, you can. And the idea here is, like, many grasping solutions are actually purely based on geometry, right? So you basically ask yourself, where can I grasp an object in a stable fashion? But there's more than that. Like, if you have a real object like this ice cream cone over here, you want to grasp it at a place that is safe for the robot and the ice cream. And that's actually what you can use these models for. And you can see on the right-hand side how LAN-grasp basically grasps the individual objects. And it's amazing how many objects there are that have certain constraints on these individual objects. And finally, like, this is 0 days ago. Right? This had been put on archive just yesterday. It's our most recent work on vacuum cleaning, right? And you can buy a vacuum cleaner that avoids dog poop. But that has been trained on, I think I heard, at least 10,000 images, right? And they all had been labeled by experts, right? Or expensive workers. And here's the LLM-based vacuum cleaning, where you can, like, in a zero-shot fashion, no object has been told to the robot. You just ask the model, should I clean or should I avoid, right? There's all kinds of things that you can do with these systems. And here's a few examples. If you can't see them, yes, that shows the power of these systems, right? So I think we are right now at an inflection point where we actually need to dive deeper into this and basically do something like the work that Vincent mentioned yesterday, this OpenMax embodiment paper, and go further with this and basically use these systems and develop them to build embodied robot systems. So I hope I also rang the wake-up call bell for you, and thank you for listening.
Great. Questions for Wolfram?
Thank you very much for the wonderful talk. One question, you talked about robotics pipeline, but from a decisional point of view, that's okay, it's a pipeline. But physical interaction is not. It's a bidirectional things that goes along the time. And I think that there is a big challenge for our community to bring this there, because if you want to do, highly dynamic things like Sangbei showed the other day, then, this is not just a pipeline. This is a bidirectional physical interaction. Could you comment on that?
Yes, that's a wonderful question. Janos mentioned that yesterday as well. And I think that it's only a matter of, like, how often you do this cycle, right? You can basically do this while you're manipulating things, right? And there's no reason why you couldn't use a large language model for detecting as to whether you still have this object in place. You can even use them for predicting how it would feel to grasp this particular object. And you can reason about stability of these perceptions in order to figure out as to whether your grasp is successful or your object is slipping through. Right? There's a super great potential for using these techniques for these purposes.
Great. Thank you, Wolfram.